So now we'll move to the second in-mode paper called ViSig, Automatic Interpretation of Visual Body Signals Using On-Body Sensors. We have the presenter, which is Ashutosh from Georgia Tech. Here we go.
Hello everyone, I'm Ashutosh Dhekne. I'll be presenting our paper called ViSig, Automatic Interpretation of Visual Body Signals Using On-Body Sensors. Where visual body sensors signals are everywhere. Think about crane signaling, how construction workers work. Think about umpires and referees on a sports field. Think about aircraft marshalling, or even flag semaphores trying to navigate ships properly. In all, just in the United States alone, more than 600,000 people actually use visual body signals on a daily basis, and cumulatively, they control billions of dollars of worth of equipment. Okay? Now, what happens when the interpretation of body signals is not correctly made? Well, disasters. Right? We have construction disasters. We have times when aircraft gets into a ditch instead of on the taxiway, or autonomous vehicles not able to follow directions given by law enforcement officers. Right? And things become a little bit more funnier when in this day and age, aircraft marshalers have to go through questionnaires when there are accidents, and then those questionnaires answers are matched with those that the pilots provide. So we're thinking, is there a way to provide a feedback mechanism to the one who is giving the signal, which tells the signaler, this is the signal you're trying to communicate, is that correct? Right, and maybe it's not just about feedback. You also want some sort of record keeping, some sort of auditing, and potentially a new system or new way of communicating with autonomous systems like cars. Even labeling of events in video streams would benefit from being able to automatically interpret body signals. Now, the current traditional approach is to try and use a camera and look at the signaler as if this is from the viewer-centric perspective. Right? When there is a single camera, of course, there can be problems such as occlusions. Now, this person is making actually a different gesture, but because of the camera placement, you may not be able to see that. Multiple cameras can be used, indeed. It requires a significant amount of classification system and so on, and has still problems when you have camera-denied scenarios, such as fog, heavy dust, smoke, etc. Of course, there exist systems which are on-body and signaler-centric. These are wearable sensors. You could use IMUs. However, with IMUs, it is hard to tell differences between some gestures, such as hand down versus hand up. An IMU on the wrist will not be able to distinguish between these scenarios. And that's why the traditional approach is to put IMUs everywhere on the body. So some of the joints will show the movement, will show orientation changes, and you'll be able to tell what the signal means. But our goal is to try and create something that has accurate interpretation, that provides accurate interpretation, real-time interpretation, very quickly be able to detect what is the signal, provide this setup with some amount of data efficiency, not throw away 99% of pixels and give 1 byte of data, and using just a small number of sensors. It's a wearable system with on-body sensors. Those transmit data to a system that is sitting next to this person, and then that can eventually be used to create records, do feedback, show it to audience, and so on and so forth. And here is the key innovation. We say that by using on-body sensors, and actually by measuring distances between these sensors using ultra-wideband radios, we will be able to produce a bounding box around the person, which is easy to interpret and easy to understand what this person is trying to create, the signal that this person is trying to create. Once we have a system like this, of course, we do need some inputs from IMUs, etc. We create a UWB plus IMU system, which is placed at 6 positions on the body. This is integrated with photodiodes on the hand so that we can also understand finger gestures. And together, we can send all this data using UWB-based communication to a system that is sitting nearby, which performs all the analysis. Now, of course, I will not have time to go through all of the details, but we'll focus on a few. One is the distances, another is detection that a signal is occurring, a body signal is occurring, interpretation of what that signal is, and then finally, understanding the state of the fingers to finally provide the output. Okay, let's quickly look at the data rate. When we say we are going to use UWB devices, these are radios, they transmit some messages, and it takes time to transmit these messages and receive replies back. The typical UWB ranging system looks something like this. You have two devices. You require ping, pong, ping, 3 messages to understand the distance between these two devices. If we were to use this mechanism for all 6 devices on the body, it would take forever to perform the pairwise distance measurement. Instead, we have devised a new technique, a new MAC protocol, which uses just a single message being broadcasted to everybody, all of the sensors. These are all on body, remember, so you don't have problem of occlusions or you don't have problem about communication range, etc. And you do the same with every node to create a ON complexity algorithm, which gives everyone distance with respect to everybody else. And because these are actual messages, we can also overload on top of those messages UWB data. And therefore, somebody who is interpreting this signal can just easily compute what's happening. Okay, I have more details in the slides, of course, than I will have time to go through. But the first module that we need is a signal detection module, something that tells us whether this is a signal or not. And think about this scenario. We have a few defined, well-defined signals, and any other movement of the signaler is to be ignored. So the amount of data that is to be ignored is so large that we can't even train for it. Therefore, we have a simple classifier which tries to train for just the signals and say, let's cluster all of the signals inside a small circle. Sorry, my laser pointer doesn't work. But inside that small circle, you have the blue spots, which are the signals, and everything other than the signals have to be kept away. That's the red dots. If that's not happening in the training set, we retrain, creating a loss function based on that, and eventually create this kind of a metric, which has to be defined per application. After that is done, we have a rather shallow network to try and figure out what is the specific signal that a person is trying to give. And finally, we have finger detection of how many fingers are up by using photodiodes. A lot of details are there in the paper, of course, and you should look at them. We have collected data with a few participants. There are 11 total signals in cricket, baseball 13, crane 20, flag, semaphore has 30 signals, and football has 47 signals. Together, when we perform machine learning-based evaluation, we get an approximate, the worst case accuracy is about 95% for football. There are 47 different signals. The best case is somewhere around 98%, etc. Remember, this system has to just work with a particular person, does not have to work across people, but we have done both of those experiments. So thanks so much. Final thoughts? Maybe you can use UWB to solve some of your own problems, so come talk with me. Thank you so much. I'll take questions.
All right, we can take one question.
Yeah, so thank you for the nice presentation. I just have one question. The system looks a little bit impractical in the sense that what if I cannot put the sensor in my head? Does this affect the bounding box that you're creating, and how are you analyzing it?
Good question. It is a little bit specific to the application. If your application does not have movements with respect to the head, it might still be able to survive with a fewer set of sensors. Some applications just require hand movements, for example, and 3 sensors would suffice, just 2 on the hand and 1 on the torso, which does not move.
Okay, let's thank our speaker again.